to start the lecture. Today, I want to talk more about compactness that we introduced last week, and I want to talk about equivalent definitions of compactness. So there are different ways, different properties that are related to compact sets, and they can be used to define compactness, but they're also interesting in and of themselves. So as an introduction, let's just look at something that happens in R. And if you were a student in my section last quarter of 131A, you saw this example. You may have seen it in other sections as well. But this is just a statement in R. You don't have to use compactness or anything to understand it. So let us consider some intervals. In equals a and bn, so an is less than or equal to bn. And these are nested intervals, meaning that a2, b2 is contained in a1, b1, and etc. They don't have to be centered, but they have to be closed and nested inside each other. So this means that, well, of course, an is less than or equal to b, and that's to make these intervals. An should be increasing. The left-hand points are going further to the right. And then the right endpoints are decreasing, meaning that they are going further to the left. And what can be shown already using 131 techniques is that if you take the intersection of all these sets, that this intersection is not empty. And this type of statements, they are actually quite in higher dimensions. They have a lot of applications. So I'll give you one visual representation of this before we go into the proof of that statement, and that proof will just be 131A material at this point. You could, this is in the plane. You should imagine the screen as being the plane. And here you have the screen, the Zoom screen that's iterated in itself. So you have these smaller and smaller screens that seem to go until infinity, but there is some point in this horizon that belongs to all of these squares. And this is sort of like the statement that we have here, except that this statement is one-dimensional, whereas this figure is showing something sort of two-dimensional. Okay, so we want to show that this intersection is not empty. Now, question, how do you prove something like that? How do you prove that an intersection, possibly infinite intersection of sets, is not empty? Any ideas? Either in the chat, you can unmute yourself if you feel brave.
Well, one idea is, so you have the ANs, which have a limit, right, as they go to the right, and the BNs have a limit as they go to the left. So you'd want to show that, in a sense, there's a space between where they limit.
That's right. Yes. Thank you very much, Josh. So Josh suggested that, well, these intervals seem to become smaller and smaller. These left endpoints are moving to the left. And in the limit, it would seem that they would limit to some interval where the left endpoint would be the limit of ANs and the right endpoint would be the limit of BNs. Okay, that's fair enough. So actually you could show with this that the intersection would be some interval itself. But something else that one can extract from this idea is that if you want to show that something is not empty, we're not even showing that it's an interval, it's enough to actually just find some element. And this idea of looking at, say, the left endpoint is a very promising idea. So the idea is to find some element, because if there's some element, that means, as I said, it's not empty. And how we will find this element is we will look at the limit. So limit, so let A be the limit, n goes to infinity of an, or equivalently, because it's an increasing sequence, the supremum of an. These both give the same value. Well, okay, because an is increasing, then a will be bigger than or equal to an for all n. This is, I mean, one could add steps here. Okay, an is less than or equal to a for all n. Well, since all of the AMs are less than AN, less than BN for all M and N. I mean, at least pictorially, one could show this directly using these inequalities that we gave, but pictorially, all the left endpoints are to the left of the right, any right endpoint. Sorry. So we have that for every pair of indices AM and BN, AM is less than or equal to BM. So if we take a limit in M goes to infinity of AM, that is less than or equal to BN. Well, this is just the limit of ANs with a different dummy variable. So A is less than or equal to BN. So what we get from these two steps, this one and this one, is that A is less than or equal to BN is bigger than or equal to AN for all n. And this means that A is inside the interval AN, BN for all n. Because it is in all of these intervals, it means that it's in the intersection. So A is in the infinite intersection of these intervals. And we should have n in natural numbers. Any questions on this? So far, we haven't said anything about compactness, closeness, or anything else. We haven't connected it to the notions of this class. But our goal, one of our goals will be to generalize this statement in some meaningful way to metric spaces. Okay. So yes, yep, go ahead.
Why do we need the AM here?
The AM is, well, if I would have, if I would use just AN here, AN less than or equal to BN, then I couldn't take a limit in N because left and the right n side would depend on the same thing.
Oh, I see.
Because I want to take, but if I have an M here, and I take a limit in M, I can take a limit on both sides, but then the limit on the right-hand side becomes a limit of a constant. So that's why I want to introduce, I mean, what that step is just arguing is that, okay, say B2, it's to the right of all the A's. So whatever these limit to should be to the left of that.
Okay.
But that argument requires taking a limit of A's and holding B fixed, and that's why I introduced these two indices there.
Thank you.
Yeah. Of course, as was indicated earlier, there are other points in this space. I mean, you could take the infimum of Bn as well. Say infimum of Bn, or in the worst, anything between these two values. Actually, anything between those will be in the intervals, just as this was saying. That's fairly easy to show from these properties, but okay, I was just interested in proving that it's not empty.
I have a question about the proof.
Yes.
So when you say, you say that AM is less than or equal to BN for all M and N, and then go on to say the limit is less than BN.
Yeah.
Couldn't you say that you couldn't do that because the limit of the AMs could be bigger than any individual AM?
That's correct. So let's expand on this a little bit. Thank you. So if I take the limit on both sides, in M, so then we get limit as n goes to infinity of AM is less than the limit as m goes to infinity of Bn, which is just Bn on the right because Bn is a constant. and limit of am as m goes to infinity is a. So we get that. So you're right. Yeah, this requires an argument. So what I'm using here is a lemma that if I have some two sequences, an, and now I'm using n's as the that I'm taking the limit. Well, let's use m's because am and cm are two sequences that converge. Then, and these are all real numbers, then you can show that limit as m goes to infinity of am is less than or equal to limit as m goes to infinity of cm.
All right, thanks.
Yeah. So this is a, yeah, I won't now go into this. I can return to this at the end of the lecture if somebody wants to recall that, but okay. So we would like to generalize this property to metric spaces. And as a first step, we need a basic thing about closed and compact sets. And this is a phrase, this is a theorem. So if we have a metric space, X, we have some subset of it, that's K. And then we have some closed subset inside there, E. And this closedness, it doesn't really matter, but it's the closedness in X. Actually, in this case, because it's the subset of K, being a closed subset of K in its relative topology is the same thing as being closed in X. But if this part confuses, just assume closed in X. It won't make a difference for this statement, which is the case. Then E is compact. So any closed subset of a compact set, it says self is compact. Okay. Proof of this. Well, what do we have? We have to prove that if we take a sequence of points in E, so let xn be a sequence in E, then we want to find a convergent subsequence. To find that convergent subsequence, well, we have to use our assumptions somehow, and this has to converge also within E. Okay, well, where could we get convergence? We know that the subset is compact, K subset of X is compact, and E is a subset of K. So since E is a subset of K, xn is also in K. It's a sequence in K. Now, since K is compact, then there exists a subsequence, X and K, that converges to some X that is in K. The point X, we know that it lies in K because K is compact. So that is that limit K goes to infinity of X and K is equal to K. Okay, so by choosing some of the elements, we get a converging, something converging. This is not enough yet for proving that E is compact, because we actually also need that the limit point X is in E, and by what we have stated, we only know that X is in K. So how could we conclude that this point X is also in E? Well, we have to use some other assumption that we have, namely that E is a closed subset that we haven't used yet. So since X and K are points in E, which converge as k goes to infinity to x, then since E is closed, that means E contains all of its limits, and X is a limit of this particular subsequence. Then since E is closed, we know that X is also in E. And this concludes our proof, because we have found the convergent subsequence, X and K, that converges to a point X in E. So E is compact in this case. Okay. Well, this is a sidetrack. Yeah, go ahead.
The notation there is a little confusing because you have this set K, then using as K approaches infinity. Can you just clarify? Is that just a big K versus little?
That's a big K versus little k. Let's avoid this whole issue and put an L here. So as L goes to infinity, this way we don't. Yeah, I guess that those are the 4 instances of little k's. So now we have L going to infinity, and the subsequence is NL. So then we don't. Yeah. Thank you. And one more. Yeah, there was an XL. Yeah. So the sequence is indexed by numbers L in natural numbers, and this is a little L. Yeah. And these are points in E. So some points in this set that they won't show very well in this picture, but I draw it again. So K, E, and then we have this some subset of points that bounces around here, but eventually it has to accumulate to something, but it can't escape the set E because E is closed. Other questions? Okay, so we needed this is needed mostly to be able to state the next theorem in a slightly nicer way. Okay, so I want to say something about generally if I take intersections of closed sets, that these intersections would be not empty. So we have a theorem that if K is a compact space, I'll draw a picture. So we have K is some compact space or compact set, and then we have a family of closed subsets within it. So K1, K2, K3, and they form this kind of a Russian doll kind of thing, that they can become smaller and smaller as you go, as n becomes bigger. So how to state this rigorously: if K is a compact space, and if you have a sequence of closed non-empty subsets, such that all of them are subsets of K. So this is the first condition. And then the second condition is that they form a decreasing collection. That is, K1 contains K2, contains K3, contains K4, etc. So such a collection is called of sets is called a decreasing chain, or just decreasing collection of sets. And you could express it with indices as if n is greater than or equal to m, then we insist that Kn is a subset of Km. And just like with the intervals, or with the two-dimensional picture that we had, or as this picture indicates, the conclusion of this theorem says that, okay, this intersection can this time be quite complex, but it has to be not empty. So relating to our earlier discussion, in the R case, it's very simple to see what the intersection is. In higher dimensions, it's not so easy, but it's still true. Okay, well, how to prove something like this? And we could take one of the ideas that we had from before is that we could try to find, we have to find some point. Find a point in the intersection. And that way we will show that this intersection is not empty. There was a technical glitch in the recording so that the audio from the second half of the lecture did not appear, which forces me to re-record this portion of the lecture. Where it interrupted was in this theorem statement that if we have a compact set K and we have a decreasing family of compact subsets, so K is a subset of K, and sets become smaller in that for larger indices, the set will be a subset of the previous ones. And for such a decreasing collections, and the crucial thing here is that these are not empty, the intersection of all of them will be non-empty. So to draw a picture of this, consider we have K, and we have some subsets of it, and we should draw these as somehow becoming smaller and smaller. The intersection, and as we take a limit of these, or send them to infinity, we imagine that there's some collection of points. It usually is infinite, or often is infinite, that is contained in all of these sets. So we want to show that this collection is not empty, and just like before, it suffices to find some point in the collection, in the infinite intersection. And just like before, we will find this point by taking a limit of some points. So, well, we don't have special distinguished left or right endpoints in general. So we have to just arbitrarily choose these. And this is done at the second stage of the proof. Well, since Kn is not empty, it contains some points. Now, each of these Kn's, for every n in natural numbers, is not empty. So that even though there are infinitely many, we allow for the ability to choose one from all of them. This point in principle requires the axiom of choice, which we permit in this class. So certainly for each individual Kn, we can find some element Xn. We allow that this choice can be made for all of these sets simultaneously. Well, what this gives us, it gives us a sequence of points. So returning to our picture, what this sequence of points looks like, I'll draw it in purple, is that we're taking a point in the first set, we're taking a point in the second set, and third set. Now, if these sets become smaller and smaller, then these actually converge, but they don't have to converge in principle. And that's where, well, we want to make them converge. And that's when we need the third part of this statement, when we bring in compactness. Since K is compact, we can find a convergence subsequence indexed by some L in natural numbers, where we only select the indices NL. And it being convergent means that there exists some X in K, such that the limit converges to that limit of X and L. As L goes to infinity is equal to X. So this gives us the X. Now what we want to show is that the X actually belongs to our intersection. So X is the limit object that we are thinking of. So we have to show that it belongs to all of these sets. So we fix an N. Now there exists an L such that once the indices are far enough, that all the indices in the subsequence will be bigger than or equal to N. And why this is true is, well, the subsequence goes off to infinity. This is often this kind of step is often something you use when you prove something about subsequences. So that's good to memorize, that you often need to write that out. Now, by construction, we have that each of the x and L are contained in K and L. So it's contained in K and L, but we want it to be contained in N. And this is why we were looking at this NL bigger than N, because when N and L is bigger than N, K and L is a subset of Kn. So X and L is also contained in Kn because it is contained in K and L. And this is true for all large enough indices, because for those large enough indices, we had that property. Now, X and L is contained in Kn. That means that X and L plus 1, X and L plus 2, X and L plus 3, ... they're all contained in Kn, because these are all indices that are bigger than L, capital L. Now, when we're taking only the large indices, that is indices bigger than something, this is called the tail. And X is also a limit of this sequence. And because all of these points lie in Kn, then the limit point has to also lie in Kn. Why? Because Kn is closed. So we get that X is in Kn. Now, why this was necessary to do carefully is that we don't have that all of the elements X and L lie in Kn, but only for large enough ones. But most of the time, for limits, this does not pose an issue. So what we have shown in the 3 steps, we found an element X such that for every n, X is in Kn, because it was a limit of a tail of elements that were in n. And that means that lie is the same thing as lying in the infinite intersection. And that means that the infinite intersection is not empty. Now, one small thing about the tail. Now imagine you have this was asked during the live lecture, is if you have a sequence of points, x1, x2, x3, ... and then somehow converging to x. I mean, we had to go to the subsequence, but so the tail just means that you take some of these elements at the end. So this is called the tail of the sequence. And why the tail? Because it's the tail end. Only indices L, say, bigger than capital L. That's always called the tail. And if the original sequence converged to X, so does the tail converge to X. So this is often a very useful thing. And many facts about convergence are only dependent on the tail. This is also true. You saw this similar thing in Math 131A, in that the convergence properties of a sequence only depend on indices large enough. And similarly, the convergent properties of a series only depend on the tail of its defining sequence. So some facts we were using here, just the proof is complete now, but just to highlight these. Well, we were using the fact that if E is closed and you have a sequence of points in there, then the limit point is also an element of E. This is the definition of closed. But the technical thing here is that this requires that the full sequence is in E. Now, what we get in the proof is we get a subsequence is in E, and only for large enough L. So here, E is our K, and if you compare it to above. And this is what we call the tail. And we still know that, well, we know that the sequence conversion, but we only know that membership for large enough indices. And one trick to overcome this and to get still that X is in E is you could define, if you wanted to be fully rigorous, you could define a new sequence, YK, And this time, yk would be an E for all k. And limit as k goes to infinity of yk would be equal to x. You could show that. And okay, so when do you encounter things like this intersection business that we just discussed? Well, it arises a lot in fractals. So one construction is that of a Sierpinski triangle, where you start from a triangle and then you cut out these white portions. And you're left with these figures that arise from iteratively removing central triangles. And they become self-similar in that they contain pieces that look exactly like the big part, but they contain them at every scale and location. But how it connects to what we discussed is that these block sets, they form a decreasing sequence of compact sets, and this fractal object is actually defined as an infinite intersection of things. And by what we have said, this infinite intersection actually will be not empty. Now, there are other constructions similar to that. If you remove the white squares in this figure, so these are always central squares of a certain subdivision of this object, and you can probably see the pattern and how these are constructed. But as you go from one step to the next, what you get is a decreasing sequence of compact sets. And the ultimate object, the fractal, is an infinite intersection of these. And what we have just shown is that this is not empty. Of course, the picture very much suggests that it's not empty, but it leads to some very interesting pictures. And so this kind of intersection business is actually somehow very crucial for much of the type of geometry and analysis that, for example, I study. Now, for those of you who are studying computer science, there is a nice fractal connected to the XOR operation. Now the XOR, so-called exclusive OR, and that's where the X comes from, means logically either X or Y, but not both. And so the truth table related to that is 0, 0 gives you 1, 0 because neither are true, 0, 1 gives you 1 because only one is true. But if both are true, then we get false. So it means either or. Now, you can create some nice pictures if you take a point in the unit square, you express it in its binary representation, so both of them will become binary strings, 0 1s. And then you take a bitwise XOR of these elements, meaning that, well, you apply the truth table to every bit. Now you have 0, 0, you should get 0 here. 1, 1, that would give you 1, and etc., etc. So small issue here that this should be 0. And etc. Yeah. Here you have, yeah, no. So 0, 0 would give you 0. 1, 1 would give you, I got my period in the second one is here. So 0, 1 gives you 1. 1, 0 gives you 1. But then the third index here is 1, 1, which gives me 0, for example. We need a fourth index here. So 1. Okay, so what you can do with these and where the fractal comes in is that if you take xy and map it to bitwise XOR, so this function, and you take its graph, so this gives you a new number in 0, 1, and you map it in R3. The graph of this function actually results in fractal, where you do a similar construction as before, but with tetrahedra. And it has a very similar behavior that arises from a intersection of compact subsets. And one can show, well, by what we just showed, it's not empty. So these pictures actually do come up even in relation to some very natural operations like XOR, exclusive OR. So that gives a nice connection to, say, computer science. Okay, so we get that intersections of certain collections of sets are not empty. What if you drop these assumptions? And our main assumption in the statement was that our collection K was compact, that is, K is closed and bounded. Of course, we also had the assumption that Ki are closed, but let's ignore that for now. You could also come up with a counterexample related to that. So if K is not bounded, then what we could do as a counterexample is take K to be the set of non-negative real numbers, so 0 to infinity. Well, this is closed but unbounded, so therefore not compact. We could define Kn as all the numbers bigger than or equal to n, but this time the intersection of all of these sets would be empty because there is no number that's bigger than or equal to all n's. Example 2. K is not closed. Well, in that case, we could take the open interval 0, 1, and we could define Kn as the half open interval from 0 to 1 over n. Now, a point that is Kn OK is not closed, but it is closed in K. And why? Because Kn is equal to the intersection of the closed set with K. And we had a theorem saying that intersections of closed sets are closed in the subset. Now, if you take the intersections of all these half-open intervals, that means all the numbers that are between 0 and 1 over n, then again you get empty sets, the empty set. And this can be represented by, we have 0, and then we have this set of endpoints marching to the left. Well, in this time, well, we would guess that, okay, these are converging to 0, but 0 is not in any of them. So the limit point is not in there. And that's where we need really closedness at some point in there. We need it both for K and we need it for Kn, but first we need it for K. Okay, so I would like to talk about this property for general subsets. Okay, we need compactness. This is somehow very close to compactness. So we introduce a so-called finite intersection property that looks a bit similar, that involves intersections of sets. But how it is, so we say that K satisfies the finite intersection property if for all collections of closed sets, so Fi is closed and we have some collection, I and I, if the full intersection is empty. So if there's no point that belongs to all of the Fi's and K, then there actually exists already finitely many of them for which the intersection is empty. And it's useful to think of the case I equals n, and that's what we really can focus on. That will mostly be our focus. So what we have here is we have the black set here is K, and we're taking an intersection first with F1, then with F2, then with F3. And what we're left with is these intersections that become smaller and smaller. So first this oval, then this triangular shape. And as we take more and more sets, the intersections become smaller and smaller. And what we're saying is that at some point, these intersections become empty. And that means that this is true. So this formulation might be a little bit confusing. In the proof of this, often we work with actually saying that if K, and how it connects in more directly with what we've done, if we're looking at the infinite intersection being empty, then we really say that, I'll use an index little l here, then there exists a capital N such that K intersected with the first N of these is actually already empty. This looks a little different because here you're taking the first N of them, but there's really nothing so dramatic about this, because if you take K, comparing this to above, if we define Kn as being K intersected with L equals the first N of these, and let L be maximum of I1 through I little n, the collection of points that we have here, then K intersected with the collection of Fik is actually contained, or contains, K intersected with the first N of these. Because here, each of these sets is actually also one of those sets. Therefore, we have that. And if we conclude that this is, if we conclude that this is empty, then that forces this also to be empty. So usually this formulation is actually enough. It's implied by the first one at least. So let's focus on this formulation. This is not quite equivalent to the full finite intersection property, but for metric spaces, this is enough. And I want to show this special case. So that's an example. So K is compact, I is natural. I want to prove that K has the finite intersection property. With I equals n. We don't prove the full case in this part. Okay, well, how do we proceed? We will proceed by proving by contrapositive. Now suppose that we had, for all finite collections, non-empty intersections, and I would like to say that the full intersection is not empty. This is the contrapositive statement here. Now, all the finite intersections are not empty. That means that if we take the first n of these and define Kn, and this is motivated by what we just said, that these are a little bit easier to analyze, then what these are? Well, these are closed because they're intersections of closed sets. They are decreasing, meaning that if you take more sets, then you get a smaller set. And we know that they're all not empty. Well, then, by theorem, we know that the intersection of them is not empty. But what is the intersection? The intersection is K intersected with all the FKs, because here you're adding more and more sets. And we know, therefore we know that this intersection is not empty. And this concludes the contrapositive proof. You could also formulate this as a contradiction proof if you wanted. Now, this was all about closed sets and intersection of closed sets. Now, for every property that you have for closed sets, there is usually an analogous property for open sets. So there's a way to translate properties from open sets to closed sets. And often it involves, if you have some intersections of open sets, they become unions of open sets. If you have that the intersection of closed sets Fi is empty, then this should correspond to the full space or full set being a subset of Vi. And the sets themselves become complementary. So unions become intersections, sets being empty intersection that corresponds to actually covering the full thing, and the set corresponds to its complement. And this last one is something we've seen because a set is open if and only if its complement is closed. So this gives us a connection between properties that are expressed in open sets and closed sets, and that's why I'm looking at the last part of this lecture with open covers. And I want to start with examples from R to emphasize what I mean, what kind of properties I'm looking at. And first, let's look at the open interval 0, 1. If you can cover the thing by intervals from 1 over n to 1 minus 1 over n. And these form this increasing collection of open sets. And remember that decreasing kind of turns into increasing in this case. That covers the whole space. But what we need notice is that you really need all of these sets in this union. If you take any sub-collection of these, you don't cover everything. But a different behavior occurs if you have the closed interval 0, 1. And if you cover this closed interval with some open intervals an. We observe that even if there are infinitely many intervals initially, then by a proper choice of intervals, we can always find some sub-collection of them that will work. We first cover 0, then we cover the endpoint of that interval, then we cover the endpoint of that interval, etc. Now, there are special cases where things don't quite work out this nicely, but it turns out that the conclusion is still true, that you can always find a finite number. In this case, there were roughly 6 of these intervals that cover the whole thing. So you never need infinitely many open intervals. And so one could say this, that the game always ends in finitely many steps, and finitely many of these are always enough. So let's be a bit more rigorous and define what I mean. First of all, an intuitive notion, if K is a subset of X, if you have some collection of sets, Vi, I, and I, then we call this collection of sets a cover if K is contained in the union. And cover is, as a picture, is very intuitive to represent. We have this black set, we have some collection of red sets, Vi, and they should cover, literally cover the set. Every point should be contained in one of these sets. And that's a cover. now, and what we saw here, these were exactly covered. This is a cover of the open interval 0, 1. So what we saw is that here Vn is a cover of the open interval 0, 1. And then here we postulated that we have some cover of the closed interval 0, 1. And because of the presence of these endpoints and being able to cover them, then in the latter case, you can actually have finitely many. And we say that, we try to generalize this property, we say that a subset satisfies the open cover property if for every open sets Vi that are a cover of K, there exists actually finitely many of them such that K is contained in the union of these sets. And it's really good, I think, useful to compare it to this finite intersection property, is that here we have the full thing is belonging into the union, and previously we had that the intersection was empty. And these are indeed somehow dual or notions to each other. So all this discussion, where is it going? Ultimately what we want to get is that we want to give a theorem that says that a subset K is compact if and only if one of the following equivalent conditions holds. First, we have the sequential compactness. This is our class definition. Every sequence has a convergent subsequence. This is obviously an if and only if because it is the definition. But then there are two others. In terms of open sets, we could say that a set is topologically compact if K satisfies the finite cover property. And we could say that it satisfies the closed set condition if K satisfies the finite intersection property. Or you could just say the finite intersection property says. But the three things here that we introduced, these intersection of closed sets, this covering by open sets, and this sequentially compactness, these are all equivalent to each other. And this means that when you're using compact sets, you can use any of these three in your proofs. Usually you use only one of them, and most of the time you'll only use one. But you'll find in the literature, especially in Rudin, a lot of proofs that also use 2 and 3. If you're taking 121 concurrently, you'll find that actually this second one, and why it's called topologically compact, is usually the definition used for topological spaces because it avoids referring to sequences, and whereas when sequences are more appropriate as a tool to study compactness in metric spaces. At this point, I will not discuss the proof of this. This will be done in the Wednesday lecture, but I wanted to introduce that there are these 3 equivalent conditions that could all be used as defining compactness. There will be some Q&A from the original lecture that I will leave in the recording, but this is the end of the replacement portion.
And even though this statement is a little bit more general, it's probably much more concrete to think of. So definitely think of I as being equal to N. In principle, you lose well, for metric spaces, you don't lose any generality, but from topology, for other cases, you do lose a bit of generality for that. But okay, let's think of I equals N. So what do we have here? We have K. We have F1 is some set. Then we have F2. And we are taking iteratively the intersections of that. So first we have this blue part, then we have this red part, and then we keep on adding sets. F3, etc. And what we're saying is that, okay, at the limit of this sequence, we're left with nothing. And if we're left with nothing, then at some point, our picture had to look like this. That this is F, say at the fourth step, F4, because this doesn't intersect the previous intersection at all. That's the only way to actually have no points in here. And the reason, well, one of the directions is that these intersection sets form a decreasing set of closed sets inside a compact space. And as they become smaller and smaller, eventually there has to be some point inside there. Now, yeah, I think I mean, these properties, okay, they might, for some of you, might seem a little bit appealing in and of themselves. I think it would be fair for most people to say that why in the world would anybody consider any of these properties, the finite intersection property or the open cover property? They, at least when I first saw them, they were completely unnatural to me. The reason turns out to be that even though they're abstract, even though they're not intuitive initially, they turn out to be very convenient for writing some proofs. For certain proofs become very short and very quick to write if you have this powerful language to use. So they really capture something about compactness that's not shown by the sequential property, and that's useful for certain proofs. And that's why we're introducing them now, and that's why we're spending a little bit of time trying to understand what they mean, why they're true, and the relationships between them. And it also gives us a chance to practice these notions more. Scroll down to the, yes, so we had the contrapositive. We defined these finite intersections of taking the first n of these. Now, they are a decreasing collection. Well, and decreasing non-empty set. These are not, yeah, decreasing, closed, and non-empty. Therefore, by the theorem. In practice, you use, so in a single proof, you use only one of these properties. So you choose, when you start a proof with compactness, you choose which of these three you will use. And you'll do that depending on whichever is easiest or whichever you feel most comfortable with. So you never need to use simultaneous, or at least I'm not aware of a context where you would simultaneously need to use multiple properties of compactness. For a lot of the basic facts that are discussed in this class, you could also do a proof in any of the three, starting from any of the three assumptions. However, some of the proofs will be much more intuitive than others. One good example is actually extreme value theorem that we will hopefully get to on Wednesday. And there, I think our sequential definition actually gives the easiest proofs. And most of the time in this class, I would start from the sequential definition. Probably the open cover is the next one I would try. So eventually, if you've seen enough practice, you get fluent and you get a sense of which one you want to use. You maybe get a preference also. So some people prefer to use one of them instead of the other. It's somewhat a matter of choice which you use. There is also a sort of general art. It's not really fully precise, but since these three properties are equivalent to each other, then in principle, any proof that uses one could be rewritten to use another. Now, that's not fully rigorous statement, but it is true in the sense that, of course, by rewriting the proof to include the proof of the equivalence, you could do that. But so since whenever you have equivalent properties, it means that any proof using one could be written to use the other. However, sometimes proofs read better when written in terms of one definition than written in terms of the other. So, yeah. Okay, that was a lot. Any other questions?